to the afternoon session. So in today's session now, we'll look upon XRD. What is XRD, how X-rays are formed, how X-rays would interact with the matter, how they diffract, and what pattern we'll get, and how to analyze the pattern. So these things we would like to see in this session. If we see, X-rays are one among the electromagnetic spectrum. They are after UV rays. They are located over here. So they have low wavelength, means they have high frequency. And if we compare this one with the energy, if you know, like everyone, Hc equals to Hc by lambda. So lower is the wavelength, higher is the energy. So these rays are contains lot of energy. If we see the history of it, X-rays are discovered in 1895 by German physicist Röntgen. And at that time, they don't know what nature of these rays are. They don't know whether these are wave pattern or they are particle made of things. So they don't know what type of rays are these. So since they don't know, they have kept it as name X like an unknown thing. Hence the name X-ray. These rays are invisible and they travel in straight lines. And these are, as we said earlier, like these are part of electromagnetic radiation. Of exactly the nature of these rays are something similar to light, but they have very short wavelengths. The short wavelengths that we are talking about are in the range of 0.5 to 2.5 angstroms. If we see how these are produced, X-rays are produced when an electrically charged particle, here we say electron, with a sufficient kinetic energy, if it like this highly electrically charged particle, which we are referring to as an electron, has higher kinetic energy. Again, kinetic energy K equals to half. Anyone can tell that? Hello? Okay. So if a particle that is moving with such a high kinetic energy, if it rapidly decelerates and hits a particular target, then there are X-rays that emits from the target. We'll see about that again. If we have an X-ray tube, the X-ray tube consists of a source of electrons, the place from which these electrons are produced, and then two metal electrodes. Why are these two metal electrodes required? Metal electrodes, I mean like an anode and a cathode. We'll see why an anode and cathode are required again. So there is high voltage because to maintain a high kinetic energy, a high voltage is maintained. And at a high voltage, which is maintained across two electrodes, we'll get thousands, like typically sometimes thousands of volts. These will rapidly draw the electrons towards the anode. So the anode is the target and the place where the filament that is used to produce these electrons are called cathode. So usually we'll have a tungsten filament or any other filament which can have higher amount of, like, which acts as a cathode, and through that cathode um the electrons are passed towards the anode, which is the target. So source of electrons are two types. One is the ionization of, like, you can have source of electrons through ionization of small quantity of gas, and you can also have filament tubes, which acts as source of electrons, which is a hot filament. These produced electrodes, these produced electrons will draw towards the anode. Anode is your target, and then they will hit the anode. That point is called point of impact. And after the point of impact, now several rays are produced from that because it has rapidly decelerated over there. Those rays are called X-rays and they radiate in all directions. So most of the kinetic energy of electrons striking the target is converted to heat, and less than 1% is transformed to X-rays. Now if we see this one, we'll have better idea. So this is a sealed X-ray tube, and this is the tungsten filament, which is the source of electrons for us. This tungsten filament is connected to a transformer. So you have really high voltage that is provided over here. And this is the target that we are talking. The target can be either a copper target or molybdenum based one. Now there is difference between the voltage between this anode, which is the target, and cathode, which is the source of electrons. So the electrons are drawn towards anode at a higher speed. If that voltage is not maintained, then this speed is not maintained over here. So once they are drawn towards this target at higher speed, means the electron with a higher kinetic energy is coming towards the target, it will hit, and the impact is so significant that on this copper, if the target is copper, copper can have different electrons at different orbitals that it can have, right? So it can replace that electron from orbital also. And then several X-rays are emitted. These X-rays can be emitted at all directions, and we need to have these beryllium windows over here. Through this, the X-rays can come out of this X-ray tube. Is that clear? And vacuum is maintained because when these electrons are moving, they don't want these electrons to interact with any other material over here apart from the target. So to do so, they have kept, like, it is necessary to keep this entire system under high vacuum. This is one thing. And since high voltage is maintained over here, and these are hitting at a very high rate, like at a very high speed, this entire system would have higher temperature. So to cool this system, there should be a continuous cooling water that should pass all across this. So there is this cooling mechanism which is also necessary for this. And these windows should allow the X-rays to pass through this, but they should also withstand the vacuum. So only beryllium would satisfy both of these conditions, and hence we have beryllium windows through which X-rays, the emitted X-rays from the target would come out through this sealed X-ray tube, and those X-rays we use as source X-rays now. Those X-rays will come and interact with the matter that we keep. Now, once they interact, they will either scatter or diffract, and the diffracted rays we will collect through a detector. Then we will get a pattern. So the rays from the target are found to consist of mixture of, like, once they studied what are these rays, they understood that these rays consist of mixture of different wavelengths. So if they see, like, they have obtained what is the X-ray intensity and the wavelength, this is the collected X-ray intensity. They have seen that when the voltage that is maintained in the tube is low, till certain wavelength, they didn't have any ray. After wavelength only, they have some rays, like some intensity that they can capture. This is from a molybdenum target. Now, once they increase the voltage from 5 to 10, what they have observed is they can start seeing the intensity even before, at lower wavelengths when compared to the 5 voltage one. And then slowly, sorry, this is not voltage, this is kilovolts, 5 kilovolts, 10 kilovolts, and all. This kilovolt is the voltage that we are maintaining across this cathode and anode. So once we come to 15, then the short wavelength limit. Short wavelength limit is the minimum wavelength through which, like, below which will not be seeing any intensity of the X-ray. After which only we can see the intensity of the X-ray. So as we increase the accelerating voltage, it has been observed that the short wavelength limit has decreased towards the lower wavelengths, and also the position and the maximum of the of this intensity has been shifted. Okay, but one interesting thing is they have seen that this spectrum is continuous, right? The intensity is continuous till here, till 20 kilovolts. So at 20 kilovolts, if you see, it is a continuous polychromatic. Polychromatic means you have several wavelengths that are that you are capturing, or it is a white radiation. This is also called as a Bremsstrahlung radiation, which is because, like, it is a German word for saying that as a braking radiation, because it is caused by electron that is decelerating in nature now, or decelerating in movement. But if we see at 25 kilowatt, you can see that there are two peaks that are coming. Why are these peaks coming, and are these peaks are interesting to us, is what we are trying to see now. Is this clear till here for everyone? No? Yes or no, please? Because this would be a bit more detailed. Okay, let me know if you don't understand. We can like please stop me at any point of time. We can discuss at that point and then we can move forward. Okay, assuming that we can move forward now. I wanted to see this one so that I'll understand how much. Okay, yeah.
You can continue, ma'am.
Yes. Thank you. No, I wanted to see this. This used to come as a side panel where I can see the participants. That is not coming now. Okay, I'll move forward. So what we have observed in the previous slide is we can see that there are few characteristic peaks that are coming at an accelerated voltage. Yes, please.
Slides that you're talking about is not visible.
Yeah, sorry. Is it visible now?
Yeah.
Yeah, thank you. Sorry. So what is happening over there? Why we are getting this sharp peak and what that sharp peak means to us? So beyond certain voltage, whatever sharp intensity peak that we are seeing, which is dependent on the voltage that we are providing, these lines are characteristic lines, and the cumulative, like the total of all these characteristic lines, will give us a characteristic spectrum. As discussed earlier, we have a filament. From filament, we are getting electrons, and those are hitting the target. Now assume that this is the target. Target will also have a nucleus and electrons in different orbitals. Now that electron which is coming from the filament towards the target can also hit one of these electron that is already present in the orbital and kick that electron out. Once this electron, for example, if that moving electron that is coming from the filament is kicking out an electron off the target over here, then this entire atom would be in a metastable state. To come back to the normal state, now the electrons from the higher orbital shell will move and occupy this vacancy that is created by hitting electron. Once this is happening, then there is a radiation that is emitted. That is what we see as that characteristic peak that we have observed. That is intensity. So if from L shell, if it is coming to K shell, then you have K alpha radiation. But to satisfy the vacancy of K shell, if some electron from M shell is moving and occupying, then we'll get K beta radiation. Similarly, we'll have L alpha, L beta. And if something from M shell, if it is kicked out, then something else will come from the next orbital and occupy that place. That would give you M radiation. So you'll have K radiation, L radiation, and M radiation. You can have K alpha, K beta. You can also have K alpha 1 and K beta 1. That is what is shown over here. So now we understood why these peaks are coming, right? These are characteristic lines. We have K beta and K alpha. We can also have K alpha 1 and K alpha 2. But we have seen that the X-ray intensity peak is a continuous peak, right? Continuous peak means you have several wavelengths that are satisfying over there. Means it is a polychromatic one. But we don't require polychromatic wave for X-ray diffraction experiments. For X-ray diffraction experiments, we need monochromatic wave as much as possible. To get a monochromatic wave, now we have to remove either one of these. Either we have to eliminate K beta or eliminate K alpha. We provide one filter called nickel filter, which has some absorption coefficient, and that nickel filter will filter out the K beta peak. But while filtering out the K beta peak, it it will also reduce the intensity of K alpha peak. So that is the trade-off that we have to do. We can get rid of K beta peak to have a monochromatic wavelength, but we'll also have a reduced intensity of K alpha peak. So there are several filters, like something similar to K alpha, what we have seen. There are several filters that we use in the diffractogram. So this is the X-ray source. X-ray source means what we have seen, the sealed tube. This you assume as a sealed tube, and these you assume as a beryllium windows through which your X-rays are coming out. Now these X-rays are coming out in all directions, right? So to have those X-rays which are coming only in parallel ways, we provide solar slits. So solar slits will ensure that the X-rays are only parallel X-rays are passed through. And the X-ray that is passing through the solar slit will then again move through another slit, which is divergent slit. Divergent slit will now determine how much portion of the sample should be radiated by this X-ray. So the width of the divergent slit is important for us to understand how much area of sample are we radiating with the X-rays. So now from the X-ray, from the sample, we'll get diffracted X-rays. Those diffracted X-rays will again pass through anti-scatter slit. This will work something similar to divergent slit. And again, we'll have X-rays in all directions. Only to collect those X-rays in parallel direction, we have solar slits, then detector slit, and then we'll have a detector over here. This is how various slits are important for us and various filters are important for us to ensure that we are having a monochromatic X-ray that is passing from the source to the sample, and also monochromatic X-rays that are collected towards the detector. So how do they interact with matter? How these X-rays which are uh, hitting on a sample, or how do they interact with the matter that we're talking? Matter here means any of your material. Material can be amorphous material or crystalline material. It can be solid material. It can be liquid as well. So how do these interact with matter? X-rays are scattered elastically. Like there are three types of interactions. They can scatter elastically, they can scatter inelastically, and they also can get absorbed. So the absorption is dependent on what type of matter you have, dependent on the atomic number of the matter. Heavier the atom, higher is the absorption. Lighter the atom, lighter is the absorption. What do we mean by scattered elastically and scattered inelastically? Scattered elastically, we mean that the scattered waves will not have any change in wavelength or energy. But when it is inelastic scattering, there will be decrease in the energy and also increase in the wavelength. Before understanding that X-rays can be used to determine what is happening within the crystals, people started using, even before understanding what is the nature of X-rays, they started using to produce radiographs. Radiographs are something which will help you to tell whether there is any crack in the bone. Like this is like you have a petrographic photographic plate. You have your target or your any body that you would like to study, and on the other side there is the X-rays that are passed, and the passed X-rays through the sample is captured on your photographic plate. That's how you will capture these images. Then they started studying to understand whether there is presence of any cracks in your bones or any metal casting to and to see the internal part of the matter which cannot be seen with the naked eye. But significant improvement has been made in 1912. That is the first place where the X-ray diffraction by crystals was discovered. And this diffraction has also proved that the X-rays have wave nature. And then they understood that they can use these wave natured X-rays to investigate what is the fine structure of the matter. Means like what is the crystal structure that we are talking about. So in 1912, Van Leeuw, he is a French scientist, hypothesized that something similar to the matter, if we have crystals which were composed of regularly spaced atoms, which can act as a scattering centers for the incoming X-rays, And if X-rays were electromagnetic waves of wavelength about equal to interatomic distance, then it should be possible to diffract X-rays by means of crystals. You understood? Not all X-rays will diffract. Only few X-rays whose spacing is equivalent to the wavelength of X-rays, those X-rays would be diffracted by the crystal that is present over there. So then, like this is the hypothesis. To prove this hypothesis, he worked with Friedrich and Nipping, and they studied the crystal structure of copper sulfate. They placed the copper sulfate in the path of narrow beam of X-rays, and a photographic plate was kept on the other end, and they recorded the presence of diffracted beams. They understood that through this experiment that X-rays have wave nature, and they also see the periodic arrangement of these atoms, which also talks about what is the crystal structure that we are talking about. Later, two other scientists, a father and son, W.H. Bragg and his son W.L. Bragg, found interest in this one, and they started proving and coming out with the necessary conditions that are applicable for diffraction to happen. Both Van Leeuw and W.H. Bragg and his son W.L. Bragg, they got Nobel Prize in Physics for this invention. Now we'll see what do we mean by diffraction. So if we have a path, if we have an wave that is coming like this, and if it is a straight line, we have two waves that are coming, and towards the other wavefront B dash, we can have constructive interference if these two path lengths are same. But if we are increasing the path length of wave 2, then at wavefront B dash, the wave of is the second wave and the third wave won't be in same phase. There would be difference in the phase. That phase difference is because of the path difference that is there. So the differences in the length of path will lead to the differences in the phase. And the differences in the phase would lead to change in the amplitude. If you see, now the amplitude is not the same amplitude of 1. The amplitude at the wavefront, which is cumulative of these two waves, is less because of the extra wave path length that wave 2 has traveled. So now we see that if there is a difference in path length, there can be difference in the rays. So there are various ways where the path length can be differ in the actual crystal. If you see, this is the crystal. We have different planes in the crystal, and in each plane, these black dots are the atoms. We have several atoms in the each plane, and we are radiating this with X-rays that are coming from XS wavefront and that are scattered and measured at YY wavefront. If I consider the wave 1 and wave 1A, now wave 1 is interacting with an atom that is positioned at K. And once it interacted, there is a scattering, and the scattered wave is 1 dash. Now we have another wave 1A, which is interacting with atom P. After interaction, it has taken the path 1A dash. Now if I see the path difference between wave 1A and 1A at X and 1A dash and 1 dash. Now 1A dash and 1 dash will have a path difference which is equal to the extra paths that each wave has traveled, right? So if I see till Q point over here, both wave 1 and 1A has traveled equal path length. But after Q, the wave 1 has traveled extra path length of QK. Similarly, the wave 1A has traveled extra path length of PR. So the difference in the path lengths are now QK minus PR. Now what is QK? QK is, if this is theta, you'll also have theta over here. And QK would be PK cos theta. If this is PK, QK is PK cos theta. Similarly, PR is also PK cos theta. Now, is there any path difference? The path difference is 0. Okay. Now, if you consider the interaction of these X-rays with two different atoms at two different planes, consider path 1, consider another path 2, which are interacting with atom K and L. Now, the extra path or the path difference that the wave 2 would travel is summation of ml plus ln. This summation of ml plus ln is 2d sine theta. The scattered rays will be completely in phase, or constructive interference would happen only if the path difference is equal to the whole number of the wavelength of X-ray. So n lambda should be equal to the path difference, and the path difference here is ml plus ln, which is summing up to 2d sine theta. So if n lambda equals to 2d sine theta, then only you will have scattering which is completely in phase. This is Bragg's law. And we use Bragg's law day in, day out while analyzing X-rays. So if we see the interaction of X-rays with a crystal, which is highly ordered, in that case, at different, like if you can understand now, at different thetas, you can have like this wavelength is the wavelength from the target that we are talking, that is constant. And at different two thetas, the interplanar spacing of the crystal is constant, so d dash is constant, and you can have at different two thetas, you can get different waves that can be captured or scattered or diffracted, right? All those waves you can accumulate, and this is the way that you will get. This is intensity versus two theta values. You'll have all the diffracted X-rays intensity captured through the detector at various two theta positions. If it is a liquid or amorphous solid, which doesn't have any orderly arrangement of atoms, in those cases, you'll not be having a defined peak like this. And if it is a monoatomic gas, then there is no structure at all, then you'll not be having any defined peak and defined peak position as well. But if you see a crystal, for example, over here, which is NaCl, you have peaks at different HKL spacings. HKL here 111, 200, 220, 311. At all these different HKL spacings, you have different peaks. This is one such example of calcium portlandite, which is calcium hydroxide that is present in the system. We have not done with OPC, it's only calcium hydroxide that I am showing over here. But this calcium hydroxide is doped with some amount of zincite, which is zinc oxide. So not all peaks are of calcium hydroxide, but few peaks are of calcium hydroxide. Nevertheless, if you see the peak shape or the peak shape, you can see these peaks are sharp in nature. They are not broad. This is because calcium hydroxide is a crystal. It is not an amorphous material or poorly crystalline material, something similar to calcium silicate hydrate. NATS is another internal standard that we generally use while quantifying the XRD, quantifying the phases from XRD analysis. And NATS is a highly crystalline material, and you can see how the peaks are over here. They are at defined peak positions, and the peaks are also sharp enough. If we say like where do we use XRD in cement analysis? Cement is also a crystalline material, and it can produce XRD pattern. And the diffraction angle and the position of the peaks is determined both by symmetry and the size of the unit cell. The intensity is now related to what is the nature of the material, what is the position of various atoms within the material, and the composition. This is used to quantify the degree of hydration in cementitious systems and also to understand what different types of hydration phases were present. Say like in TGA, we have only seen whether any decomposition is happening or not, whether there is a weight loss or not. But what is this weight loss all about? Why is this weight loss is happening? If we see XRD of cement, OPC cement, unlike CH and NATS, in NATS we have seen sharp peaks at defined 2 theta positions, but over here if you can see OPC, you have lot amount of peaks which are at different positions, right? At different position here, I mean 2 theta values. This is one other thing where this is the XRD scan of Portland cement, and the peaks that are given at the below are the matched peaks. So this is your pattern that is obtained from OPC, and this is the matched peaks. Like C3S, they have matched the C3S peaks with the peaks in your sample. They'll see at what peak position. So this is your 2 theta position. At 2 theta position in your sample, there is a peak. Even in C3S, there is a peak. So is this corresponding to C3S peak? Is what we see when we are qualitatively analyzing XRT patterns. So then if you have C2S, C2S has peaks in other 2 theta positions. C3A has positions here, periclase here, anhydrite or here. So like that, we will keep on adding each mineral. Each mineral will have peaks at different positions. We will match whether the peak at that position is present in our sample or not. Through that, we will try to understand what is the unknown crystalline or unknown phase that is present in our sample. This is search match that we do. And these are the XRD patterns for fly ash. In fly ash, we have mullite as one of the phase. We have quartz, we have hematite, and the remaining portion is unknown element, or it can also be amorphous nature of your XRD. Sorry, amorphous nature of your material. Over here, the amorphous nature is accounting to somewhere 59.3%. If you see XRD of silica fume is highly reactive material, right? If a crystalline material is there, crystalline material won't be highly reactive. Amorphous material is highly reactive. Over here, silica fume is highly reactive, which is amorphous in nature. That's why you'll not be seeing sharp peak, something what you have seen in fly ash, something similar to what you have seen in fly ash, but you'll have a hump or broad peak like this. This is a classic example of the presence of amorphous material in your sample. From XRD, you can tell that. And these are other XRD patterns for different other materials. The top one is CDW. CDW is construction demolition waste. In construction demolition waste, since it is crushed material, you'll be having andesite, diopside, which are coming from the aggregates from the concrete of the demolished concrete. We can also have CSH, mullite, calcite, quartz, waterite. These are all we obtained after matching. We have also quantified it. This is fly ash, which you have seen earlier. GGBFS is also an amorphous material. That's why you see a hump over here. What are these peak positions? What are they telling us? And on what parameters are these peak positions? When we see XRD, we bother about three to four different things. First is at what position we are having peak. And what is the peak intensity? What is the peak shape and peak width? These three are most important. Apart from this, we'll also worry about what is the background. Now we'll see what are different powder diffraction variables like peak position. Peak position is mostly dependent on lattice parameters of the unit cell. Like you will have a unit cell with A, B, C as your lengths and alpha, beta, gamma as your angles, right? So lattice parameters would define at what position your peak will have appear. Now how the lattice parameter is defining that? Lattice parameter will also define what is the, like, can anyone tell? Okay, lattice parameter will tell us what is the position of atom as well. And the position of atom in the unit cell would provide us what type, like, to which wave the matter is interacting with. And there is one more thing called 0 point correction. So you have your diffractogram, like your goniometer circle and the detector. It is not always that the initial angle is 0. Angle here, I mean 2 theta value. Like there can be your equipment error, that is 0 point error, means we are not starting with absolute theta of 0. Another one is sample height displacement. Usually we load the samples as a backloading one. Powder samples are the samples that we use. We'll have disc. In the disc, we'll fill our powder. We fill the powder on the back side, we'll compress it, and then we will front load it. So back loading is usually done. But when you are scraping the powder that is filled in the cell, if you have not maintained parallel height, or if the height is bit above, that would interfere with your theta angle again. So that correction we should make. These are all corrections that are there in the program, but if we don't ask the program to do these corrections, then it will not do. So we should be aware of what corrections one has to do. Now coming to peak intensity. Peak intensity is dependent on various factors like scale factor. Scale factor is dependent on the equipment again. Then we have Lorentz and polarization factor. Lorentz polarization factor is cumulative of a Lorentz factor and the polarization factor. Polarization factor talks about what if the X-rays are not polarized? What if X-rays of unpolarized nature comes and interact? So to accommodate that, we have polarization factor, and Lorentz factor will talk about, like, is it necessary that at a particular theta only we need to have the diffraction? Say that your n lambda equals to 2d sine theta has been satisfied when the theta value is somewhere near to, for example, 20. It is not that at 19.8 will not be having a peak. There will be some intensity. It's not that at 20 only we are having a line peak. We are also having a, like we have seen in the last slides, right? We are also having a, like over here, if you see, the peak is starting at this particular 2 theta's values, right? And then peak has been peaked at a particular 2 theta value. But the shape of peak is not a single line. It has been broadened and narrowed down. So that is taken care by your Lorentz factor. And then we have multiplicities factors. We can have different HKL planes which are giving us this interaction. So we have multiplicity factor. We have absorption factor. Absorption factor is mostly related to the type of atom that is present. We have preferred orientation factor. When you have all the crystallites that are arranged in a single pattern, single nature, or aligned in a single nature, then also that will affect the intensity of the peaks that you capture. The atomic position and the occupancy of atoms that are present in your unit cell will also affect the peak intensity, and other displacement parameters. Displacement parameter over here is, you are assuming that the atom would be present at that particular position in the unit cell. But it is not true in nature. Because of thermal fluctuations, the position of atom at any position, at any place is not fixed, right? It keeps vibrating, it keeps moving, right? So this displacement parameter would take care of that. Peak shapes can be of, like, you can have a sharp peak, you can have a broad peak. It again depends on various parameters. And background, to address the background, you can always use a polynomial. Polynomial either to 3 to 5 terms is sufficient, not lower and not more than that. Again, if we see in detail, peak position is determined by size and symmetry of the unit cell. This we have discussed. Peak intensity is determined by position of atoms in the unit cell. Peak intensity is what we worry more about, or what we are concerned more about. So for a crystalline phase in a powder sample, the intensity is dependent on Sj is your scale factor, Lp is your Lorentz polarization factor, A is your absorption factor, Pj is your preferred orientation factor, and F is your structure factor. Now the structure factor is dependent on various other parameters again. Peak width is influenced by the microstructure. So this peak width is influenced by 3 different sources, like, or 3 different ways. One is through your sample itself, one is from the instrument, and one is from the source. Now, if we use fundamental parameter approach, now we can remove the contribution from the instrument and the source, and we can have peak width from the sample itself. When we talk about peak intensities again, peak intensities, we have discussed about scale factor, Lorentz polarization factor, absorption factor, and preferred orientation. If we see structure factor is the one which carries all the crystal structure information. Here we talk about how many number of atoms are there in the unit cell. and it is dependent on the atomic form factor. This is atomic form factor is dependent on how strongly an atom can scatter the electrons, sorry, scatter the X-rays, and at what position these atoms are positioned. Say um, if it is any like if you have 50-50 phase compositions or solid phase, in that case, you will not be having occupancy of that particular site by this atom as 1. It can vary from 0 to 1. And this parameter is the interference parameter, which is mostly talking about the location of atoms in your unit cell. That is why you have HKL, which are HKL parameters, and X, Y, Z are your fractional coordinates. Okay, HKL from your Miller indices, X, Y, Z are your fractional coordinates. And the temperature effect or the atomic displacement factor that we are talked, that can be taken care by Debye-Waller factor, which is exponential of minus Wn. Now we have our pattern. We know what influences the peak position, what influences the peak intensity, what influences your peak width. Now, if we would like to determine the unknown crystal or unknown peak that is present in the XRD, or if we would like to quantify how much amount of phase that is present, then we can do one refinement, which is called Rietveld refinement. What is it all about? Rietveld refinement will do, like you have intensity of your material, which is your observation, like why I observed, right? This is intensity at each data point that I'm talking about. And then if you think that this material can match, for example, if you have OPC, OPC has several peaks at several 2 theta values. Now, if you guess that, okay, there may be a possibility that Portlandite can be present. Now, if you load the Portlandite peak to that file, now it will take the intensities of Portlandite. It will try to minimize the difference between your observed and the calculated one. And then it comes to a scale factor. This is your Rietveld refinement scale factor. And the main objective of Rietveld refinement is to minimize this. Is to minimize this entire difference. Then only it is like your calculated is as near to your observed value. Now, what are different values or different factors on which this calculated intensity is dependent upon, or how is it obtained? The calculated intensity, because it is of several phases, or like we are talking about crystal with several phases. If we take all those phases, we have scale factor of those phases. For example, J1, one is one of the phase that we are talking about. That phase can have different peaks, right? Again, if I come back to OPC, OPC will have Portlandite. We have seen that Portlandite has different peaks at different 2 theta values. Now, all those peaks are considered in this second accumulation that we are talking about. So, P equals to 1 to the nth peak of that Portlandite phase is what we are considering, times MPJ, LPP, again, Lorentz polarization factor, FPJ here is structure factor for that phase. This factor talks about the peak shape, which is either the difference between your, or which can be either a Gaussian function or a Lorentzian function or a pseudo-Worket function. And this is the preferred orientation plus the background that you are considering. This we have done for all the peaks for one phase. Like that, we will calculate for another phase. And then we will keep on adding several phases. The cumulative of all these are taken over here. And then we'll try to minimize this scale factor of the Rietveld refinement. This is what the entire objective is. So the parameters which are refined in the quantitative phase analysis are either global parameters or space-specific parameters. Global parameters, we have background and the sample displacement correction. Sample displacement correction we have seen earlier, either regarding the zero position error or the height of the sample. This talks about the height of the sample. And we also have phase specific parameter. Phase is like you can have several phases in one particular crystal. The phase specific parameters which are related to scale factors that can fit to observe to the observed peak intensities. You'll also now have unit cell parameters which can be refined during quantitative phase analysis. This will do to fit the peak positions and the shape of peak profile function. Towards the end, we can also correct the intensity through preferred orientation. Now we are fitting something, right? How do we know that this fit is good or bad? How do we know that we are fitting, converging towards a solution or we are diverging from the solution? To that, there are different goodness of fit parameters that people have arrived at. We have R Bragg value. R Bragg value talks about the difference between the observed intensity with the calculated intensity divided by observed intensity. Since we have intensity that is coming from various phases, this will not help us much when we are trying to understand whether we are refining it in a right direction or not. So we rely more upon RP. RP talks about the intensity of each data point rather than the entire intensity at that position. So we have yi is the data point. We consider each data point, the data point that we take at different step sizes. So we have yi observed minus yi calculated divided by yi observed. And this will not be having any uncertainty. We have not considered any uncertainty in picking up the intensity of that at that particular data point. If we consider that and if we provide some weight for that, then we'll have like weight factor. Then we have RWP, which is residuals of weighted profiles, which is equal to sigma of yi observed minus yi calculated square by sigma of yi observed square. And then we have RXP. RXP is M minus N, where M is number of data points that we are considering for the refinement, and N is number of parameters that we have refined. The parameters are here are either the global parameters or your phase specific parameters or your unit cell parameters. The goodness of fit is now defined as the ratio between RWP and RXP. And we say that fit is perfect when this value is converging towards 1. This is what we look for. These two are like we'll have our eye upon like whenever we do refinement, whether we are decreasing the RWP value or increasing the RWP value. So while starting your refinement, you'll start with one RWP value and we'll see as we keep on including the phases into your data, are we decreasing it or are we increasing it? Now we'll get Rietveld refinement scale factor, which is this SY we are talking, right? This SY can be directly related to what is the amount of weight fraction of that particular phase. From there, we'll understand what is the percentage of different phases that is present in your sample. This is how we converge towards the quantification of XRD or quantification of phases. So the scale factor that we obtain is directly related to a factor K times Wj. Wj is the weight fraction of that particular phase. Rho j is the density of that phase. Vj is the unit cell volume. And mu m is the sample mass absorption coefficient. Sample is the entire sample, not the phase only. So from like we know Sj, we know rho j, Vj. We cannot be getting Wj because we don't know K and mu m. K and mu m are constants. So we cannot directly determine the phase weight fraction only through Sj. So to get this, what we do is we add, like we either sum up all the phases, like we have Wj as one phase, like that we can have n number of phases in the sample. We'll sum all those and then say for a crystalline material, the sum of all phases should be equal to 100. Once we say that, we'll eliminate K and M, and then we can get weight fraction of a particular material. But this weight fraction is considering you only have all the phases. So it would be an apparent weight fraction, right? Because you are considering the entire summation would be equal to 100. Or you can either do an internal standard method or an external standard method. These two are coming only to eliminate K and mu m so that you can relate Sj directly to the Wj value. In internal standard method, what we do is we add some amount of internal standard or any crystalline material with known crystallinity, and it's not some amount, it is the known volume or known amount. Say if you are taking some 3 grams of your cement. To 3 grams of your cement, I am adding now around 0.3 grams of a crystalline material. The crystalline material that I am taking over here would be either NATS or corundum. Corundum is Al2O3, NATS is TiO2. So now when I'm submitting the sample for X-ray analysis, or when I'm doing performing XRD, I'll be giving a sample which is a mixture of 3 grams of your OPC plus 0.3 grams of your internal standard. Now we'll get the peaks. The peaks will have both the peaks that are coming from different phases that is present in OPC, as well as the peaks that are coming from the internal standard that you have added. So now you'll have Sj, rho j, Vj for different phases that are present in your OPC. And SS is the scale factor for the standard. Rho S is the density of the standard, and Vs is the density of your, volume of your standard. Now we are dividing these two so that we can, like, you have Sj for one material, you have Ss for another material. Now we are dividing these two to eliminate K and mu. That is what we are doing. So here you'll get now Wj in terms of Ws. I know what is Ws, what is the weight fraction of internal standard I have added to the material. So once I know Ws, Sj, rho j, Vj, Ss, rho s, Vs, we can arrive what is the Wj. So that is what is done over here totally. We'll have Wj equals to, again, it is assuming that if it is 100% crystalline. If it is not 100% crystalline, you'll end up having the added internal standard value higher than the Ws that is coming after refinement higher than the added internal standard amount. So if you are adding 10%, after refinement, you'll be having Ws value as some 11% or 12%. Now that difference is coming from the amount of amorphous content that is present in your sample. If it is 100% crystalline, you'll be getting 10 and 10. So that is what we do over here. Once we get all the phases, from 1 minus all the phases, weight fraction of all the phases would give us what is the amount of amorphous content that is present in the system. But there are few cares that we have. Anyone would like to talk? Okay. So we have to be careful that the homogenization of the internal standard plus your sample should be done properly. There should not be any overgrinding. The crystallinity of the internal standard should be known, because if that is not known, then everything will go in vain. And there should not be this internal standard should not be present in your sample. Say, for example, the peaks of zincite might match with some of the peaks of your, say, suppose one of the phase of your XRD of your sample. Then we'll not be knowing exactly how much of that peak intensity is from your internal standard or from your sample. So it is preferred to have the internal standard which is not present in your sample, but which will have distinct peaks or peaks at different 2 theta values than the peaks that would be obtained at 2 theta positions of your sample. So that care should be taken care of. For all the clinkers that we use, rutile is generally used, and for hydrated cement, corundum is used as internal standard. Rutile is TiO2 again. And in general, we add at a proportion of 20%, 10 to 20%. Means if you would like to give XRD sample of 3 grams, your 2.7 grams would be OPC. And if I'm considering 10%, 2.7 grams would be OPC, and 0.3 grams would be your TiO2, either NATS or rutile. So in internal standard method, we are kind of adding something to our material. We may not be comfortable with adding the material, some external material to our material all the time. In those cases, we can go for external standard method. In external standard method, what we do is we take the XRD pattern of the sample. We also take the XRD pattern of the standard separately in two different experiments, but using the same diffractometer conditions. Then we do the Rietveld analysis on that. From there, we can cancel out the K because we'll get Sj for the, which is Rietveld refinement scale factor for our sample. Similarly, SS, which is Rietveld refinement scale factor for the standard. From there, we can eliminate uh, uh, the K value, but mu M and mu S we should determine. Mu M is the mass absorption coefficient of the entire sample. Mu S is the mass absorption coefficient of your standard. There are several crystallographic tables which talk about what is the mass absorption coefficient of your sample. This is again dependent on what is the chemical composition of the sample, because it is determined on whether how much amount of calcium oxide is there and how much amount of various other chemical oxides present in your sample. And for each oxide, depending on what is the target that you have used to generate X-rays, whether it is a copper target or whether it is a molybdenum target, depending on these two, in a table, they will give what is the mass absorption coefficient. It is available on net for free. One can go over there and get the mass absorption coefficient of each oxide. Now you know what is the percentage of each oxide in your sample. By multiplying these two, you'll and summation of that, you'll get what is the total mass absorption coefficient of your sample. Like that, the same way we'll also be doing for the external standard. And from this, we will get what is the weight fraction of each phase. So the major advantage is it doesn't need to intermix anything with any standard within the material. So the entire data collection in general, if you would like to have an XRD analysis on your sample, it is preferred to have the 2 theta ranges between 7 to 70 degrees centigrade 70 degrees 2 theta for cementitious systems. We in generally use, like most of the diffractograms use CUK alpha radiation. The step size is the one which will determine majority of things, and step size can be maintained at 0.02 degree 2 theta. And it is also preferred to have particle size less than 5 micrometer, but the grinding should not, like, to maintain this particle size or finer particle size, we should not be grinding extensively, because that extensive grinding will also lead to phase transformation. As discussed earlier, it is preferred to have backloading, and as discussed in the TGA class, the way that we stop the hydration would also govern the amount of hydration products that are present in the system, and that would govern the peaks that we can see from the XRD. So this is what it is. If you have fresh slides, you can see ettringite peaks, monocarboluminate, hemicarboluminate, and then you have ettringite again, calcium hydroxide, and all these things. What they have observed is, like, with different types of storage and the hydration stoppage method, how each phase has been changed. Then this phase has been quantified using X-ray analysis or X-ray diffraction. Till now, what we have seen is quantitative. We need not do this much of procedure if we just want to know or identify what is there in our material. So that is qualitative phase analysis. Qualitative phase analysis, we mostly bank on the peak position and intensity. We'll not be worried about what is the amount, like we would not be doing Rietveld refinement over here. There are several databases to match what we have. So we use the already crystallographic information of different phases that is present in the database. We'll take that file and then we'll try to match with the peaks that are present in our sample. That is what we do in qualitative phase analysis. So the databases that are already or widely available are these. And now we'll see one such example by using Qualex software. Qualex software is also again a freeware that you can download from website, and then you can use this software to identify unknown peaks. But while using that also, we should be a bit more careful. We cannot just take whatever it is saying to us. There is another software, but it is not a free version, which is Match 3. And for the rate field refinement and for quantitative phase analysis, we have several softwares. We have Analytical High Score Plus. This we get from the instrument itself. We have MDIJ, widely used like is Topaz. GSAS is also there. GSAS is a freeware again. You can download and you can use GSAS software. Foolproof is there, Profex is there, and there are many other softwares which one can use. Now I would like to exit from the slideshow, and then I'll show you through Qualix how to. One minute. Yeah. Yeah, I'm sorry. So this is Qualix website. Sorry, Qualix software. I'll open it again. You can load your diffractogram or diffraction data by going to File, Import Diffraction Data, and then you can select any data, but the data should be either in one of these forms. If you don't have any data in these forms, what you can do is you can use Powdle converter, everyone might be knowing. You can use that Powdle converter and convert any data file to any other file extension that you would like to have. Now I would like to load annotate, open. Now we have to define what target have we used and what is the wavelength. Wavelength for the target. We have used copper here to generate this diffractogram. Copper target has been used to get the X-rays, and those X-rays were projected on this sample. Now what we can do is we can see that there is a peak at what position? Peak at 25.72 theta. We have three peaks here, peak, 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 peak. And these are well-defined peak at well-defined 2 theta positions. Now we would like to understand what is this peak? Is this exactly annotates that I'm showing? Or is it something else that I'm showing and saying that annotates? Or if you don't know what is the material that is present in your sample, that can be identified. So you have to go to search and do search match. Now search match will take the CIF files or the crystallographic information files that is available in the database and try to match the 2 theta positions of that file with the peak that is present in the 2 theta position of this sample. That's how it will do the search match. Over here, you can see it is throwing us what is the most probable match for this particular piece. So it is saying now you can have annotates. You may be having annotates in your sample. That is what it is showing. So if you click on this, if you see this corner over here, this is your experimental 2 theta and experimental intensity. This is the data of your sample. Now we are trying to match the peak intensity and the peak position from the zip file or from the file of each phase. Now if I click annotates, like annotates has this card number you can verify. Now it is saying that at 25.3, we also have peak at 25.3 in our sample. Annotates that we have clicked also has a peak at 25.3. So peak positions are matching. Next step is you see whether peak intensities are almost near or not. So this is the major peak for this particular annotates, and peak intensities are also matching. Then you can select this and consider that this material may be present in your sample, or you can identify that one as your material. Once you select it, you'll be having like, can everyone see this? Is it very clear to everyone? Now you can see this is P which one we have selected? We have selected NTS, right? This one. Now you can see that this is the position of 2 theta at which your peak is there from your sample, which is black in color. And this is the position of 2 theta in which peak is present from the card that I have selected, which is NTS over here. So these two are matching. Here it is match, 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 match. Means this particular zip file of NTS is matching with the sample of NTS that I am having. So this is one way to quantify. Now you can say that this peak is NTS, these three peaks are NTS, and so on and so forth. Now, is this clear to everyone? Is it okay? Now let us load one more sample. I'll import now CH. CH is Portlandite. Sorry, I'll exit. We'll open Corlex again. Now let us import calcium hydroxide. Again, I'll say target is CU and then I'll try to search much. Now what you can see, again here it is giving your experimental 2 theta and experimental intensity values of your sample. Now if I select this Portlandite, this one or else anything, you keep moving. Now you see this is at 18.2 and 18.06. Now let us pick up another file. This is at 18.7. So let's go with this. Or let us pick up this one. There is also Portlandite over here. Let us pick up that. If I pick up that, then I have here 18.0 to 18.07, almost near over here. So let's try to include that phase in our sample. Now you see over here, you have the peak positions of the peaks that are present in your sample. And if I match that one with the Portlandite, whether all peak positions addressed, like NTS that we have seen earlier. No, right? So the Portlandite here, this peak position and this is matching, but this is not there, right? So this is some other peak. This is not Portlandite now. Again, you have Portlandite peak at this peak position. So this peak is Portlandite, but there is again another peak over here where the peak positions are not matching. Means the sample that I'm showing now is not a single phase sample. It may have some other material in it. That's why we have lot of peaks which are not identified. We could only identify peaks of certain positions, right? Now let us see what other peaks can be. Now you go in an order like lower decrease in this intensity. It is telling us there can be a presence of zincite. Let's click zincite and see. Once I click zincite, now you again try to look for peak positions and matching. So this P12 theta is your Portlandite, which we have already seen. Now this is what we are seeing. The card number is 9008877. So these two are zincite peak position and like 2 theta and intensity values. We have peak 31.77, 31.74, fine, 34.42, 34.40. So you try to see like this for peak positions and also peak intensities. If you feel that this can be there, you can click and select, or you can look for another file. Okay, this appears to be more appropriate. Then I'll click on that and I would like to include in my position. So once I include that, now what all I have two files that I have added, or two cards that I have added. I have added initially calcium hydroxide And the second time I have added zinc oxide. Now zinc oxide peaks are here, 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 but still there is one peak over here which is not addressed. Similarly, there are two peaks over here which are not addressed yet or identified yet. Similarly, one more peak, one more peak. So still we have not identified all the peaks that are present in the sample. We have identified only certain peaks. For that, now again you click on calcite, another space. Like this, you have to keep on doing the search match by adding each phase and understand whether that phase is present in your sample or not. By understanding the peak positions and the peak intensities. I hope it is clear for everyone. So that would summarize my discussion on X-ray diffraction. If anyone has any doubts on this, I am happy to address.
Madam,
Yes, please.
madam, if I'm going for ritual refinement, how
Uh,
accurate is the results what we get from them? And in case I'm synthesizing some sample and I don't have enough sample for XRF, can I take the result I get from ritual refinement as a quantification?
See, ritual refinement, the goodness of fit parameters that we have discussed, right? So if you
Yes.
see after refinement, what is your RWP, RXP, and goodness of fit? So when you are refining, whether you are reducing your RWP value or whether you are increasing, see towards the end, if you only see this goodness of fit, which is ratio of these two, if you have higher values of these
Okay.
two also, the ratio would turn to be 1. If you have lower values of these two also, the ratio would turn to be 1. It only talks about how close these two values are, right? So you need to understand how RWP, RXP, and your goodness of fit are varying when you are doing your refinement. Is that clear?
Okay. Okay, ma'am.
Yes.
Thank you. Ma'am, and one more thing.
Yes, please.
Depending upon the variation in intensities of the XRD peaks,
Mm-hmm.
hello, am I
Yes, yes,
audible?
please.
Depending upon the variation in the peaks, sometimes I treat material thing and the peaks have a difference in the intensity of the peaks. Then can I prove it as a redox reaction? Does it happen with redox reactions?
Mm, I'm not sure about redox reaction. Are you talking about the corrosion and all, or what is the
No,
application
ma'am.
that you are
I found
in
such
case?
thing when like I was using laterite for water treatment.
Mm-hmm.
So I expect that redox reactions are happening there. The peaks have not shifted much after the treatment, but there is a lot of difference in the intensities.
Um, uh, maybe you should quantify because only reduction in the intensity may not tell that your phase has been reduced a lot. So once
Okay,
you
ma'am.
do
So
the
ritual
ritual
refinement
refinement
would
and
help.
do the quantify, yes, yes, it might help you in the right direction. You quantify the phases towards the
Yes.
end rather than just banking on, because if you have a crystal, you can have a sharp peak over there.
Okay.
Yes.
Okay, ma'am.
It
Thank you
doesn't
so
mean
much.
that
Thank you.
the amount of that crystal is higher. That's what it is.
Okay.
Yes, yes. Thank you. Thank you very much.
Thank you,
Anyone
ma'am.
else has any doubt?
Excuse me, ma'am.
Hello.
Ma'am, I have a question. Like,
Yes, please.
if I have a sample containing 75% of OPC and 25% of fly ash, and if I have one more sample of 25% OPC and 75% fly ash, will the intensities and two theta positions will be same or different? How to interpret that kind of data?
Um, the intensity would vary for sure. You are just saying it is 75 percentage OPC plus 25 percentage fly ash. So the type of material is same, but the amount of material is different. What would you like to interpret from there? Because depending on that, I can suggest whether you have to go for quantitative or qualitative. If it is only the identification of peaks, then qualitative is good enough. If
Like
it
for
is both,
quantitative, like this much of quartz is present.
but even OPC is also crystalline, right? Like if you see the XRD pattern of OPC, you'll also have sharp peaks in that. So how is quartz affecting? Okay, if you have any doubt in your refinement, maybe you can drop an email to me. We can address it over there. Okay. Is it
Okay,
about the
thank you.
process of refinement that you are stuck with, or
No, I wanted to know about like you have mentioned in one of your slides like fly ash quartz is a 22.9%, mullite is 17.5%.
Mhm.
So
that is
in the
after
similar,
quantification?
yeah. So in the similar case, if I have these two kind of different samples, what will be my intensities?
Yeah, they will change for sure because intensity is dependent on the composition, sorry, proportion of each phases also, and how crystalline those phases are. So there are various factors that would affect the intensity, as we have discussed, right? Like you have your structuration factor, you have your Lorentz polarization factor, multiplicity factor, absorption factor that is coming into the picture, scale factor, and atomic factor. There are various factors that govern the intensity.
Uh, Ma'am, one more question. Like
Please,
I
please
have
feel
a
free.
sample.
Please make it as a more, discussion type rather than one way. Yes, please.
Thank you. Uh, Ma'am, we have done XRD for my sample, and I have analyzed uh, the mineral phases using expertise core software.
Mm-hmm.
What I felt was like my peak intensity positions or two intensities. One mineral phase is a little bit identical to the JCPDS file, but some of the peaks are not identical to the same mineral phase. So can I say by matching one intensity, this mineral phase is present in my sample?
No, 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 no. Never you could match only one two theta position. You need to match all two theta positions, all like at max all the two theta positions. So that's a good point which I didn't bring out. So when you're picking up the cards that I have shown in the Qualex software also, it's not only one two peak positions that we have to see. You have to see all the peak positions almost, and you have to ensure that most of these peak positions are matching by the card that you are selecting.
If they are not matching, what is the interpretation that we have to write in a research paper?
Sorry.
If the peaks are not very much identical, then
Then you may
what is
need to
the
pick up. If you are so sure that this phase is present and their two theta values are not matching, then you pick up another zip file of that phase. So for one phase, you have several zip files, right?
yeah?
Yeah. So if one zip
And
file is not working, you pick up another zip file. You have
and
ICSD website, you have many ICDD websites. So from all these websites, rough website is also there. From all these websites, you'll get zip data, zip files.
like in expertise course software, there is one more called matching score, or there is a score given by the software whether this mineral phase is present or not, like green color, red color.
Uh-huh.
Would you please?
That I am not totally aware of. I'm sorry for that.
Oh, no problem.
But what I can suggest if you are going for identification, you look for both peak positions and the peak intensities, but never rely on only one peak position. That would be a big no. I'm sorry for the high score expert. I use mostly Topaz, so I can talk on Topaz rather than the other one.
No issue, ma'am. Thank you for replying.
Thank you very much. Anyone else has any questions?
online participants, if you have any questions, please, you can type in chat box or you can ask.
Yeah, chat box we have not seen. Yes. Do we need to add database to Qualix? Qualix, if you would like to add your own database, that is also available. Like you can add the CIF file or the card that you want to have, and then you can add your sample. I believe the database is the CIF file that you are talking about rather than the sample. Is that the case, Mr. Vivek? Yeah. There are already prefixed or preloaded databases, but if you still want to use your database, you can use. Okay, I just installed it. It is showing a dialog. This you have all these databases for inorganic material separately and organic material separately. You need to download the inorganic material file, which is of larger data, and then you have to incorporate in your Qualix. From that only it can pick up what are different inorganic phases. So for example, over here I have loaded all the inorganic samples. I'll let you know where it is. So here, if you can see, I have loaded both, but I have only selected the inorganic COD. So you try to download that file totally, and then you can load over here. I hope I have addressed that question to you. Mr. Vivek, is that clear? Okay, ma'am, if you want to use the quantified XRD, which software should we use? Quantified XRD, we can use like either high score expert that I have shown over here, MDIJ, Topaz, Jesus, Foolproof, Profex. There are several softwares or interfaces through which you can do rate-well refinement and get the quantified phase analysis. Miss Amla? Thank you. Thank you so much. Can we use match for quantification? In match, it will allow you to do quantification, but it will not give lot of flexibility to do the refinement. That is what I observed for match software. Match here is match software. Are you talking about, Mr. Vivek? Match 3, match 5? Yeah. So match 3, match 5, like you can use, that is mostly like how we are using Qualix over here to identify the peak positions with respect to cards. Something similar, you can use the match software as well. But I believe for quantification, it will not give you flexibility to refine various parameters. But nevertheless, you can give it a try. Anything else from anyone? Any doubts that you have in isothermal calorimetry or TGA can also be taken up. Any doubts the online people have?
No questions, ma'am.
Okay. No questions. Okay. Okay then. Then I'll start the other portion, which is on FTIR. We'll see what is FTIR, and then we'll close the session for today. Is that okay? We may not delve more into it, but we'll see on a superficial level. For isothermal calorimetry, do we need to use deionized water always? When you are doing any study on the paste and when you would like to understand how different materials or different hydration products are formed from the binder, and if you would like to eliminate the other factors that influence that, it is preferred to use deionized water, but provided that if you are like studying at a paste level only, and should we include superplasticizer also? So this is all dependent on what is your objective to do isothermal calorimeter. Is it that like you are looking at how the addition of superplasticizer is interacting with the rate of reaction kinetics? Then we have to add superplasticizer. It is not necessary that if your water to binder ratio is 0.4, just to increase the mixing ability, we need not add uh, superplasticizer for isothermal calorimetry. May I know what is your objective over there? Or is it that you want to replicate what you are doing in concrete and then see? Yeah. So just to replicate the concrete mixture. Now you would like to correlate from the paste and the concrete mixture? Okay, so in that case, you maintain whatever you are doing for the concrete, just remove your aggregates. Maybe the other proportions you can keep constant. Hello. Yes. Anyone else has anything? Thank you. Thank you very